Give me one afternoon today, and I'll save you 20 hours later. This is every core concept of engineering thermodynamics. Tightly edited, zero fluff, designed for 3 people. The student previewing the course, the student panicking right before finals, and the engineer prepping for the FE exam. So I spent 7 years operating nuclear reactors on Navy submarines before getting my PhD at Duke. Now I head the mechanical engineering department at High Point University. I'm joined, as always, by TA Serenity and TA Indiana, who just dove off the table there. They're cats, but still more reliable than most human TAs.
The professor will cover the theory, the demos, and the math.
Just leave the cute cat humor to us professionals.
So grab a notebook, don't write down everything, just the aha moments. And we're starting at the end, the power plant. Before we go deep on any single concept, I want you to see the whole machine first. So this is a steam power plant. Most of the world's electricity is produced using this 4-step process, the Rankine cycle. So in the real world, a power plant looks like a massive maze of pipes and cooling towers and soaring structures. But thermodynamically, it boils down to just 4 essential components. So let's track the working fluid through this cycle. First, we have the pump, from state 1 to state 2. It takes cold liquid water at low pressure and pressurizes it to cold liquid water at high pressure, which significantly increases power plant efficiency. Easily justifies the relatively small energy cost to run the pump. Next, from state 2 to state 3, high pressure water enters the boiler. It doesn't matter if your boiler is coal, natural gas, nuclear, geothermal, solar. Those are all just different ways of producing massive amounts of heat to boil the water to high pressure, high temperature steam full of energy. Then from state 3 to state 4, the moneymaker, the turbine. It's a really fancy windmill. That high energy steam expands rapidly through the turbine blades, spinning a shaft connected to a generator producing electricity. Finally, the low energy leftover steam enters the condenser. It takes less energy to pressurize water than steam, so we reject heat to the environment, fully condensing all of the steam back to water at state 1. Now, black smoke from a thin chimney, that's the pollution from coal in the boiler. But the big, clean, white, fluffy clouds from fat concrete cooling towers, that's just water vapor carrying rejected heat from the condenser. It's totally safe. It's a perfectly closed loop. Fluid goes in a circle. Only work and heat cross the boundary. And that's the core math of this course, calculating work, heat, and thermal efficiency. So for the rest of the video, this cycle is your anchor. But to analyze the macro, we have to master the micro. So let's build the foundation from the ground up.
Then I get to knock it down.
That's literally the opposite of what we're trying to achieve.
To analyze the Rankine cycle we just saw, we need a common language. In thermo, everything starts with the system. A system is simply the mass or location we've chosen to study. Look at your figure. Draw a dashed box. Everything inside the box is your system. Everything outside the box is surroundings. The box itself is the boundary. There are two main types of systems you'll see on exams. An open system, where mass and energy are both flowing. Think of a water pipe. or a turbine, or a nozzle. In these cases, we focused on a fixed region in space. We usually call this a control volume. Your TA Serenity is a control volume. Heat enters when she basks in the sun. Mass enters when she eats snacks. And mass exits when she... gross.
I prefer to be called an open system because my stomach is always open for more snacks.
For a closed system, no mass can cross the boundary, only energy. If I have gas trapped in a piston cylinder, the mass stays put. But energy, in the form of heat or work, can still go in and out. So TA Indiana resting happily inside his box, that's a closed system.
Forget what Schrodinger said about cats and boxes. It's perfectly safe in here.
You might also see isolated systems. These are a special type of closed system. Nothing crosses the boundary, not mass, not energy. We'll usually indicate this by calling the boundary rigid, meaning no work is performed, and insulated, that no heat crosses the boundary. Rigid and insulated are keywords that evil professors use to trap students, so keep your eye out for them. Now, sometimes you have to choose your system. If I draw a dashed box around the turbine, I'm studying an open system, a control volume, right? Just the turbine. If I draw my box around the entire power plant, now I have a closed system since all of the mass stays inside the box I drew. Once you define your system, you have to describe it. We do this using properties. The big three, you already know. You use these every day: pressure, temperature, volume. In fluid mechanics, pressure is usually gauge pressure, which is relative to the atmosphere. In thermo, we always use absolute pressure. For temperature, thermo uses Kelvin and Rankine, not Celsius or Fahrenheit. Small exception when you're calculating a delta T. In that case, you can use any temperature scale you want.
Just think of me. I'm an absolute unit, and when under pressure, I remain cool as a cucumber.
For volume, actually, you'll use specific volume a lot more often, which is volume divided by mass. And that's just the inverse of density. Same idea, just flipped. So high density, low specific volume. The next three properties, you probably haven't seen these before: internal energy, enthalpy, and entropy. Something to look forward to in chapters 2, 3, and 7. So when a system is uniform and unchanging, we say it's in a state of equilibrium. Thermo problems are almost always in equilibrium. But look out for two other similar terms: steady state, meaning not changing in time, and transient, the opposite, it is changing in time. A common mistake is to use steady state and equilibrium interchangeably, but these are not the same thing, and your evil professor will take points off on your test for mixing them up. So here's an example to help you keep them separate. When the temperature stopped changing, this bar is in steady state with high temperatures on one side and cold on the other. But since temperature isn't uniform, the rod is not in equilibrium. And transient can sometimes be in equilibrium, which kind of breaks your brain a little bit. So consider a nail in your car tire, a very slow leak. We call this quasi-equilibrium, where at each instant in time, you can treat it as if it's in equilibrium, but eventually your tire does go flat. That's the transient. A state is basically a snapshot of a system. Like, what are pressure, temperature, and volume right now? Those values define the current state. So Numbers 1 through 4 in the Rankine cycle figure, each of these are a state. For properties, 2 is the magic number. If you know 2 independent, intensive properties, like pressure and temperature, you have fixed the state, which means you can look up all the rest of your properties in tables. Ooh, foreshadowing, spooky. Be afraid, TA Serenity. She's very scared. If a system moves from one equilibrium state to another, that's called a process. These lines connecting the 4 points, these are each processes. Now, if a system goes through a series of processes and ends up exactly where it started, like our Rankine cycle, that's called a cycle. In a cycle, your net change in internal energy is 0 because no matter what path you took, you ended up back where you started.
Empty bowl gets filled with food. I eat it until it's empty again. That's the dinner cycle. Who do I need to talk to about the process of filling it up more promptly?
So let's get to the first law of thermodynamics, which states you do not talk about thermodynamics.
I don't think students understand Fight Club references.
Before the first law, there's actually a 0th law. And yes, they named it the 0th law because they forgot about it the first time. So if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. Same as the transitive property in math. The thermometer is system B. You use it to measure the 2 objects, A and C, and if you get the same thermometer reading, then A and C are the same temperature. So in our house, if TA Serenity steals the warm spot on the couch where I was just sitting, then she is leveraging the 0th law. She is matching my thermal state.
Hey, in this house, I'm the thermal frame of reference.
But now, the heavyweight champion, the first law of thermodynamics. At its core, it's simply the principle of conservation of energy. Energy cannot be created or destroyed. It can only change forms. Before we look at the thermodynamic side, let's quickly review the mechanical energy terms you brought with you, like from physics and dynamics. So first, kinetic energy. This comes from speed. Second, potential energy. This comes from height due to gravity. Third, mechanical work. The simplest version of this was just force times distance. But in this course, we unlock a massive hidden vault of energy, internal energy. We use the capital letter U, or lowercase u for internal energy per unit mass. Now, to be formal, internal energy is the microscopic energy stored within the molecular structure of our working fluid. It's the sum of all the microscopic kinetic and potential energies of the atoms. So they're spinning, vibrating, the chemical bonds. So when you heat them up, you are cranking up its internal energy.
Napping in the sun isn't just napping. I'm adding internal energy to my system.
Now, don't write this on a test, but internal energy is energy stored as temperature. There are counterexamples to this. It's not a true statement. But as a memory aid, if you were to think of internal energy as temperature energy, then for me, you're at least pretty close. And hey, good news. For most thermo problems, kinetic and potential energy aren't changing, so we'll be able to ignore them. In this course, we'll usually only care about internal energy. So how do we change the internal energy of a system? If mass isn't crossing the boundary, then energy can only cross in two distinct forms: heat and work. Heat, Q, is energy transferred across the system boundary solely due to temperature difference, hot to cold. If there's no delta T, there's zero heat transfer. Then work, W, it's energy transferred across the system boundary for any reason that's not temperature. Think of a spinning shaft, an electrical wire, or a piston expanding or compressing. Now, we also deeply care about the rate of energy transfer. We call the time derivative of Q, Q dot. It's the rate of heat transfer. If Q is energy in kilojoules, then Q dot is power in kilojoules per second, which is kilowatts in SI units, BTUs per hour in English units. The rate of work is power, W dot. It shares the exact same units, kilowatts, or actually horsepower in English units. Pray for SI units on your test. BTU and horsepower are awful units to work with.
I mostly pray for tuna. Results have been mixed.
Let's talk about the single biggest trap on thermodynamics exams: sign conventions. But you'll never get the signs wrong because you understand power plants. That's why we started this video with power plants first. The boiler and the turbine are the most important pieces, so both of their terms are positive. The boiler adds energy to the power plant as heat, so heat is positive when it enters the system. The turbine removes energy from the system to produce electricity, so work is positive when it leaves the system. When the system does work to the surroundings, that's positive. When you calculate the efficiency of your power plant, net work divided by heat input, both of those terms are positive.
I eat snacks, that's heat in. I kick my rocket, that's work out. No wonder I'm always at an energy deficit. This open system demands a snack refill.
All right, one more vocabulary word before the equation: adiabatic. An adiabatic process is one where there is zero heat transfer across the boundary. This happens for two reasons. Either the system is perfectly insulated, which this is not, or the process happens so incredibly fast that heat simply doesn't have time to flow. Let's look at a classic demo, the compression igniter. I place a tiny scrap of cotton inside this glass cylinder. If I push the piston down slowly, heat transfers out to the room. It's not adiabatic. But watch what happens if I slam the piston down violently. That instantaneous compression is adiabatic. Cool. Because the work was done so quickly, the heat didn't have time to escape. The massive spike in internal energy drove the temperature past the auto-ignition point of the cotton.
That flame is basically me when somebody turns on the vacuum. Adiabatic, instantaneous, panic. No time for heat to escape.
You want an adiabatic process you can try yourself right now? Smash the like button. Seriously, it takes a small amount of work, but there's no heat transfer. That makes it adiabatic. Go ahead, smash the like button. You'll see.
All right, here is the equation we have been building toward, the energy balance equation. Don't write this first equation down yet. I'm doing a small derivation. For a closed system, since no mass is crossing the boundary, the first law is this equation. Initial energy plus energy added or removed equals final energy. In thermo, we usually care about change in energy, final minus initial. So we can rewrite this with change in energy. Then substitute all our different forms of energy. And in most textbooks and FE exam problems, the system is stationary, meaning changes in macro, kinetic, and potential energy are completely negligible. So finally, this is the one you'll use. Box this equation. We've got some math problems in this video too. It's not all lecture and explosions, and we don't even have to solve them quietly because your TA Serenity can sleep through anything. So the piston cylinder, that's a closed system, no mass in or out. So I start with the closed system energy equation, delta U equals Q minus W. The system performs boundary work on the surroundings, so the 50 is positive work. Internal energy is our final answer, so how do we find Q? If you ever find yourself with too many unknowns in your equation, go back to the problem statement. Look for a key adjective that might give you one of your unknowns. In this case, insulated. This means Q equals 0. No heat escapes through insulation. Gives us the correct answer is A. The gas lost most of its internal energy because it had to use its own molecular vault to push the piston up. Huge tip. Keep a keywords list of all the words your textbook and professor use to indicate something important. Like insulated means Q equals 0 as the first one on your list.
Don't mind me, just adding another reminder to your list.
Let's do one more example problem to drive home the sign convention. This is the ultimate sign convention trap on the FE exam. Let's list our terms based on our power plant rules. There's no mass going in or out of the tank, so this is a closed system energy balance. 30 kilojoules is negative work since the paddle wheel is doing work to the system, just like a power plant pump. Positive work would require work by the system to the surroundings. So heat adds, what was that? So heat adds 15 kilojoules, so this is positive heat, just like the boiler in the power plant. And what about all those adjectives? Rigid means there's no other work terms, no boundary work, which we'll get to in later chapters. Well insulated means no other heat terms. So the double negative turns into addition. The correct answer is D. Both the heater and the paddle wheel were dumping energy into the closed space, so the internal energy had to go up. Every time energy changes forms or crosses a boundary, nature extracts a tax. You never get a perfect exchange. We quantify this performance using thermal efficiency, denoted by the Greek letter eta. And eta is desired output over required input. Efficiency is always a dimensionless fraction between 0 and 1, or 0% to 100%. For our Rankine power plant, remember the sign convention? Since the pump adds energy to the system, its work term will be negative, so it gets subtracted. A perfect cycle would convert all boiler heat to turbine work, an efficiency of 100%. But real cycles never get there. A coal power plant will have efficiency around 40%, meaning 60% of the energy is rejected by the condenser as heat out. Nuclear is even worse, like 33% efficiency. On the submarine, when we weren't spying on people, we joked that our mission was to heat up the ocean. Wasn't really joking though. 2/3 of the reactor output was lost as heat from the condenser to the ocean. And another form, we can substitute and rearrange to get efficiency in terms of heat output to heat input. To get 100% efficiency, the turbine would have to use 100% of the energy so that 0% would be lost in the condenser, so if heat output would be 0. But, sneak preview of Chapter 5, according to the second law of thermodynamics, this is impossible. Now, before the next example problem, there's another useful term of the energy balance when working with power instead of energy. To shift to rate form, take a time derivative. If the system is in steady state, then internal energy isn't changing, so box this equation now. In a steady state closed system, heat and work have to perfectly cancel each other out. So next example problem, we'll have efficiency and our new rate form. First step, net power output. We use the rate form of the closed system energy balance. W dot net equals Q dot in minus Q dot out. So 800 minus 480, net work equals 320 megawatts. Now for efficiency, there's two ways to get there. Use whichever one your exam gives you the data for. So method 1, efficiency is W dot net over Q dot in, the desired output over the thing you have to pay for input. 320 over 800, so efficiency is 40%. Method 2, efficiency is 1 minus Q dot out over Q dot in. So 1 minus 480 over 800, and that still gets us back to 0.4. 40% efficient. The 480 megawatts, that represents 60% of input energy, is all rejected as heat from the condenser. These are the big white fluffy clouds from the cooling tower. It's not pollution, it's just wasted energy. And notice, you can solve this problem without ever knowing what fuel the plant burns, how the boiler works, or anything about turbine blade curvature. The energy balance doesn't care. By defining my system around the overall power plant, I only needed to know about the energy balance crossing the boundary, not about anything happening inside any of the individual components. And that is the first law of thermodynamics, conservation of energy. So kinetic and potential energy can often be ignored. Internal energy is new. It's sort of like temperature energy, but not exactly. The sign convention for heat and work is the easiest mistake to make in this entire course. So it's always worth a few seconds to double check your signs. And lastly, professors are evil, and we like to hide important information in the problem statement. Insulated, rigid, adiabatic, and a bunch more terms you'll learn in future chapters. Keep a list of these somewhere you can find easily. You will need it. And now, if you have ever thought to yourself, I hate equations, why can't I just look everything up in a table?
I think that all the time.
Then I have got great news for you. In the last chapter, your TA Serenity helped us balance energy. Now we need to know what that energy is inside our working fluid. That means evaluating properties. And that starts with understanding what phase the fluid is in. We work almost exclusively with pure substances, materials with a fixed uniform chemical composition. Water, nitrogen, R134A. In a power plant, the working fluid is almost always water, and it changes phase throughout the cycle. 3 phases. You know them as solid, liquid, gas. For water, we usually call the gas form vapor. But for our power plant, there's actually 5 keywords you need to know that describe this liquid to gas transition that happens in the boiler, which I can demonstrate in the lab. Let's make this visual. Start with regular, normal water. This is compressed liquid, also called subcooled liquid. Same thing, two names. Turn on the heat. When it gets to 100 degrees Celsius, we are at a saturated liquid. Now, any more heat added, and there it is. The water crosses the saturation curve and starts converting to steam. So inside the steam generator is a mixture of both liquid and gas. We are in between the saturation curves. Now, the steam leaving this tube is entirely gas. It is a saturated vapor. This is the right side of the saturation curve. This steam generator can't superheat, but imagine I captured this steam and applied even more heat to it. That would keep pushing us further to the right of the curve. That superheated steam is certified, bona fide, top choice steam that is exactly what power plant turbines are looking for. And one more term for the two-phase region that exists inside the steam generator, quality, which will appear in equations as X. Quality ranges from 0 to 1, essentially the percent of water that is vapor. 0 means it's entirely liquid, a saturated liquid. X equals 1 means 100% vapor, a saturated vapor. Anything in between is a wet mixture. Quality only has meaning inside the two-phase region. There's no such thing as the quality of a compressed liquid or quality of a superheated vapor.
This definition makes no sense. The internet says cats are liquid, but clearly my quality is 100%. So there has to be a mistake.
Liquid is 0%, gas is 100%. Cats are solid. Serenity needs to stay off the internet and go touch grass.
You know I'm not allowed outside.
Let's visualize this on the most important diagram in property evaluation, the PV diagram. Pressure on the vertical axis, specific volume on the horizontal. For a pure substance, there's a curved dome shape. This is the saturation dome. Not exactly an upside-down parabola. Usually you should draw it steeper on the left and shallower on the right. So the peak is left of center. It's kind of easy to remember since volume of water doesn't change very much with pressure. But for a gas, it's very easy to change volume of a gas. So everything to the left of the dome is a compressed liquid, regular normal water. Everything under the dome is a two-phase mixture, liquid and vapor coexisting. Here, pressure and temperature are locked together. If you know one, you automatically know the other. That's why they call them saturation pressure and saturation temperature. They're a pair. So everything to the right of the dome is superheated vapor. High specific volume, high energy. And here is how your power plant maps onto this diagram. State 1, saturated liquid leaving the condenser, the bottom left edge of the dome with a quality of 0. State 2 is a compressed liquid. When it leaves the pump, it's left of the dome at a higher pressure. State 3 is all the way in the other corner, a superheated steam leaving the boiler. It's right of the dome and really high up. State 4 is going to be wet steam leaving the turbine, partially condensed inside the dome with a quality between 0 and 1. The peak of the dome is the critical point. Above it, there's no boiling bubbles during phase change. Liquid and vapor basically become indistinguishable. For water, this happens at 374 Celsius and 22.1 megapascal pressure. Now, here's an important difference between this class and real-world power plants. Many modern power plants do operate in this supercritical region above the dome because the higher the temperature, the higher your overall efficiency. But we are not really going to cover that in this class. All of the systems and cycles on your homeworks and your tests, they will all be left under or right of the curves, not above the critical point.
I don't like that we're skipping real-world use cases, but I do like that we're making it easier. TA Indiana, approved.
Before we open any tables, we need one more property, enthalpy, which is capital H, or enthalpy per unit mass, lowercase h. So remember U from like 10 minutes ago, internal energy, that molecular energy or temperature energy? You will only use that internal energy for closed systems. For open systems, you'll use enthalpy instead. When fluid flows across a boundary, through a turbine, through a pump, or a nozzle, yes, it still carries the same internal energy, but it also has to do work to push itself through the pipe. So that pressure volume term is called flow work. Because we see that combination of pressure and volume in almost every single open system problem, engineers got tired of writing them separately. So we combined them into a single property called enthalpy. As the same units as energy, kilojoules, or kilojoules per kilogram for specific enthalpy. And the best part, it's listed in property tables. You don't calculate enthalpy. You look it up. For closed systems, you look up internal energy, U. For flowing open systems, you look up enthalpy, H. Right here, right now, this is the big one. There are 34 property tables and charts in the back of my thermo book. 68 actually, since there's both SI units and English units. If you can use these reliably and find the information you need quickly, you are on track towards an A in thermo. If you can't, you will be on the struggle bus to C-Town, population U.
I've been on that bus. The Wi-Fi is terrible and the seats are sticky. You do not want to be there.
Now, if you call the whole collection of 34 tables the steam tables, everybody will know what you mean. But there's really only a big 3 tables that you'll use more than all the others. These are the 3 steam tables. Number 1, saturated water temperature table. You use when temperature is given and you know or suspect that the fluid is saturated. Each temperature row lets you look up pressure, specific volume, internal energy, enthalpy, and entropy. We'll talk about entropy more in Chapter 7. Now, why are there 2 volumes and 3 internal energies, you ask? Well, that's a great question. The left columns with subscript F apply to saturated liquid with 0 quality. The right column with subscript G are for saturated vapor with a quality of 1. The middle number, when there are 3, is just the difference between the two. It just saves you a calculator work so you don't have to subtract them manually. The second table, saturated water pressure table. It's the exact same thing, except rows are organized by pressure instead of temperature. The third table, superheated water vapor. Each mini table is a different pressure, and then rows are different temperatures. Now, there's also a compressed water table, but it's small and it's often skipped on exams. The standard accepted approach is approximate compressed liquid properties using the saturated liquid value at the given temperature, not pressure. Because water is incompressible, the pressure doesn't really help. Changing the pressure doesn't change any of the other properties. Use saturated liquid at the same temperature, because when you change the temperature of water, the properties do change. Let's learn the tables with an example problem. So step 1, what's the fluid? Steam, so that is water. Step 2, what's the phase? Is it liquid, saturated, or gas? In this case, saturated with quality of 0.6. So we are in the two-phase region between the saturation curves. Step 3, which table do we go to? We know temperature, so we go to the saturated temperature table. And step 4, interpolate, because our system isn't liquid or gas. It's in between, so we need a number in between the two numbers given to us in the table. Interpolation is the process of finding values in the table that fall in between rows or in between columns. Like, if your temperature were 101 degrees, that's not listed in the table, so you'd have to interpolate between the 100 degree row and the 105 degree rows. You'll have to interpolate literally hundreds of times in this course. You have to get good at this.
Hundreds? They should make an app for that.
Oh, there is. But you can't use it on the test because your professor is evil.
Real talk time. Your textbook has an equation for quality. Don't use it. Start all your interpolations with fractions. It reinforces physical understanding of what you're actually doing and prevents you from making conceptual or sign mistakes. Quality is the percentage of water that is steam. If 60% of the water is steam, we need an enthalpy value that is 60% of the way from HF to HG. So set up your enthalpy values as a fraction that makes 60%. Quality is H minus HF over HG minus HF. Total liquid to gas difference in the denominator, only your smaller difference to your system's value in the numerator. So plug in numbers, 1773, answer C. Let's go ahead and do that 101 degree example too. So what is the enthalpy of saturated steam at 101 degrees Celsius? I'll go to the temperature table since I know temperature. I'll grab Hg values since I know it's saturated steam, but unfortunately 101 falls in between 100 and 105, so interpolation time. Since 101 is in between two rows, we interpolate to find the Hg value in between the two Hg values we can read. So I set up two fractions. The left fraction is what you know, temperature. The right fraction is what you want to find, enthalpy. Left fraction, the 101 falls in between 100 and 105. So we set this up to form a percentage. In this case, 0.2, since 101 is 20% of the way from 100 to 105. For the right fraction, we have H minus the 2675, and in the denominator, the 2683 minus 2675. Notice how all four terms in both fractions correspond to the matching term in the other fraction. The 2683.4 is the H value at 105 degrees, and they are both in the same position of their respective fractions. So the H I'm trying to find matches the position of the 101 degree temperature I'm trying to find H for. So do the algebra and solve. H is 2677.2. This is the enthalpy 20% of the way from 2675 to 2683.
I think I get it, but how do I know which table to use?
One more set of rapid-fire examples. So for each case, identify the phase, select the correct table, and then find the specific volume. So for A, we're going to check the saturation table first. At a temperature of 300 degrees Celsius, pressure should be 8.58 megapascal. 1 megapascal is too low. Low pressure is gas, so check the superheated vapor table. 1 megapascal mini table, 300 degrees Celsius row, specific volume 0.25799. For B, if quality is between 0 and 1, you're guaranteed saturated. With temperature 100, go to the saturated temperature table, and we are going to need to interpolate. That gets us to V of 1.42. And for C, first check the saturation table. At pressure equals 400 kilopascals, temperature should be 143.6. Our temperature of 50 degrees is too cold to be saturated, so it's a compressed liquid. It's not hot enough to be boiling. I could go to the compressed liquid table, but I don't have to. Just use specific volume at 50 degrees saturated liquid, 0.001012. Remember, you have to use temperature, not pressure, for compressed liquids. Recap. First, learn which table to use. Always check the saturation table first if you're not sure. If your system is too hot or too low pressure, then switch to the superheated vapor. If your system is too cold or too high pressure, it's compressed liquid. Second, a warning. Different textbooks will have slightly different numbers in their tables.
They're each calculated based on different sets of experiments with different best fit equations. Good news, different tables are pretty much always within 0.1% of each other. So discrepancies don't usually matter.
Just use whichever set of numbers come in your textbook and you'll be fine. Never mix and match numbers from different textbooks in the same problem, though. That will cause problems. But now that you know this might explain why sometimes you'll watch a YouTube video and they're getting slightly different numbers than you. It might just be because they're using a different textbook. All right, one more homework problem, and then we'll move on to PivNert. We're going to have to look up values we need in the steam tables. So state 1, I'll check the saturation table. 1 megapascal is 1,000 kilopascals. So saturation temperature should be 179.88. But we're hotter than this, so we must be superheated. So for a change in internal energy, we'll need final and initial. So the initial internal energy is 2710.4. So state 2, pressure is down to 100 kilopascals, but we need 2 pieces of information to fix the state. I only have 1. Remember, professors are evil. So if you don't have enough information, reread the problem statement looking for those important keywords. In this case, isothermal means constant temperature. So T2 is still equal to 250 degrees. I check my saturation tables. At 100 kilopascal, saturation temperature should be 99.6. 250 degrees is too hot. So I go back to the superheated steam tables. 100 kilopascals is 0.1 MPa. So I go to the 0.1 megapascal mini table, go to the 250 degrees Celsius row, get a specific volume 2.4, and internal energy 2733. So step 3, change in internal energy. Final minus initial. The 2733 minus 2710, 23.5 kilojoules per kilogram. Final answer. This is why I said before that internal energy equals temperature energy isn't entirely correct. This was an example where temperature didn't change, but internal energy did. But it only changed a little bit, so I still like it as a useful approximation or a memory aid. It's PivNert time, sort of. Steam tables are your go-to for water. But for gases, air, nitrogen, oxygen, carbon dioxide, we have a much simpler tool, the ideal gas equation of state. In chemistry, you call this PivNert. In mechanical engineering, we don't care about moles. We use PivMert with mass. Or even better, just divide by mass and use specific volume. P is absolute pressure, V specific volume, T absolute temperature, always Kelvin or Rankine, and M mass. There are two different R's, and you have to be super careful which one to use. Make sure your units all cancel. That's the easiest way to verify that you're using the right one. The one you need is R, the specific gas constant for that particular gas. To find R, you can look it up directly, or sometimes you have to look up molar mass M and calculate it using the other R, R bar. The universal gas constant R bar, 8.314 kilojoules per kilomole Kelvin. So you know R bar isn't the one to use in the PV equals RT equation because it has moles in it. And moles are for chemists, not engineers. Don't memorize molar masses or R values. Just look them up when you need them. So, when is the ideal gas assumption valid? Low pressure or high temperature, far from the saturation dome. Air at atmospheric conditions, ideal gas, no problem. Steam at high pressure, near saturation, use the tables, not ideal gas. Also, this is important for ratio problems. If mass and R are constant, the ideal gas law simplifies even further. So change two properties and you can solve for the third. That's the recipe for most ideal gas problems on the FE exam.
Please don't mention recipes. It's been minutes since my last snack.
This is an advanced gas laws demonstrator. Inside is just air. We've got two gauges, one for volume and one for pressure. And temperature, 3 gauges, like I said. Watch what happens when I compress the air. Pressure goes up, volume goes down. If temperature holds steady, then quantity PV stays nearly constant. That's Boyle's law, a special case of the ideal gas law. We've got 2 tools in our chest so far for finding properties, steam tables, and the ideal gas law. But there's actually a third, and don't worry, it's just going to be 3. This is the last one. Ideal gas is a great approximation until it isn't. Real gases deviate from ideal behavior, especially at high pressure or near the saturation dome. We quantify this with the compressibility factor, which gives us PivZert. For an ideal gas, Z would just be 1, always just by definition. But for real gases, Z deviates from 1 depending on the conditions. Z is a correction factor that accounts for how non-ideal the gas is. To find Z, we'll use the generalized compressibility chart. It is not as scary as it looks. First, you'll usually actually see 2 or 3 compressibility charts together. These are all the same chart. They're just like zoomed in or zoomed out from each other with a different range on the x-axis. So you want to use the most zoomed in version that matches your values. Now, you'll have to do a bit of math before you can use it. The axes aren't just temperature and pressure. They are reduced temperature and reduced pressure. You calculate these by first looking up the critical temperature and pressure in a table and then dividing your actual temperature and pressure by the critical temperature and pressure. PR is the horizontal axis. TR tells you which of all the swirly-do curves you need to follow, and then you'll read Z off the left vertical axis. If Z is close to 1, then just assume it's an ideal gas. If Z deviates significantly, then apply the correction. So 3 methods: tables, compressibility chart, ideal gas equation. Which should you use? Tables are essentially truth. These are the most accurate. The compressibility chart could be nearly as good, but it's hard to read a chart to high levels of precision, so it's probably second best. Ideal gas law is the easiest to do, but the least accurate. What's that, Sleeping TA Serenity? You want more than 3 methods? All right. Number 4, the Benedict-Webb-Rubin equation has 8 empirical constants per gas. If a professor assigns you a full BWR problem in an intro thermo course, that professor is wrong and should feel bad. You can tell them, from me, they should be nicer to you.
Hey, you assign Reynolds' transport theorem to your fluids students. Don't act like you're above all this.
Touché. We've got nitrogen at low pressure. So ideal gas law assumption is valid. Normal atmospheric pressure is about 100 kilopascals. So 200 kilopascals, it's only 2 atmospheres. That's not that much. I cancel out mass and R since they don't change, and sub in what we know. We're missing V1 and V2. So reread the problem. Rigid tank. That means V1 equals V2. So we can cancel those two out also. Calculator work, T2, 600 Kelvin, choice D. If nothing else changes, double the pressure causes double the temperature. This problem type appears on nearly every version of the FE exam. Rigid equals constant volume. Start with the general equation, cancel what's constant, and solve. If you see rigid on an exam, your next thought should be, volume is constant, so volume cancels. Next example, let's look at the difference between approximation and reality. So method 1, the ideal gas assumption. I'll just look up R in my appendix and I get specific volume, 0.01039. Method 2, using the compressibility factor correction, I first have to find the reduced parameters, reduced temperature and reduced pressure, in order to use the compressibility chart. So I also look up in my appendix PC and TC, the critical pressure and temperature, do my division, get 0.812 for pressure, 1.085 for reduced temperature. Then, if I locate PR 0.812 on the bottom axis of the compressibility chart and move up vertically and look for the reduced temperature line of 1.085, which there's not one. So it's in between the 1.05 and the 1.1 line. Then read across to the right side, I get a Z factor of approximately 0.74. This means carbon dioxide at this state only takes up 74% of the space an ideal gas would. That's a big difference. So PivZert, plug in the numbers, get 0.007688 meters cubed per kilogram. If you use the ideal gas law to design this storage container, your volume calculation would be 35% too high, resulting in an unsafe or wildly inefficient layout.
That's why I always design containers the old-fashioned way, by sitting in them.
All right, TA Serenity, need you to wake up and help me out with the Chapter 3 summary. 3 critical skills from Chapter 3. Number 1, identify the phase. Use the saturation temperature or pressure as your reference. Is your state above, below, or right inside the saturation dome? Number 2, use the correct table. Saturated tables are for states inside the dome. The superheated table is to the right, and you don't really need the compressed liquid table. Just use saturated liquid at your temperature. And number 3, know when the ideal gas assumption applies. Low pressure, high temperature, far from the saturation dome. If you're not sure, use Z, the compressibility chart, to correct the ideal gas law if you need to. The tables feel overwhelming at first, but every problem follows the same 3-step logic. Identify the state, pick the table, and then read the number or interpolate to get your answer. So repetition is the teacher here. You'll need to interpolate more than 100 times this semester. Learn it properly from the start, and it will save you many hours of your life later on. So, enough theory, let's talk real application. Next chapter is closed systems. All right, TA Serenity. In Chapter 2, we learned the closed system energy balance. Delta U equals Q minus W. Now we need to actually calculate W. Specifically, moving boundary work, the kind you get from a piston pushing on a gas. This is the most common work term in any closed system. It shows up in internal combustion engines, refrigerators, compressors, the cylinder of a steam engine. Anywhere a piston is squishing or expanding a fluid.
If this box is a closed system, when I push up on the lid, I'm doing boundary work.
So remember, the old work is force times distance. Well, on a piston, force is pressure times area. So multiply that area by the distance you push the cylinder, and what you have looks like a volume. And here is the boundary work equation. Your old friend calculus is back. Don't panic. First, a units check. Pressure times volume. Pressure in pascals is newtons per meter squared times volume in cubic meters gives Newton meters, which is joules. So yes, it works out to energy. Second, and this is the big one, boundary work equals the area under the curve on a PV diagram. But watch your signs. If the path is going to the right, that's expansion, that's positive work. If your path on the PV diagram is going to the left, in compression, that's negative work. This matches the power plant sign convention from Chapter 2. Work done by the system is positive. Boundary work is path dependent, not just for signs. Two processes can connect the same start and end states and produce completely different amounts of work because they trace a different path. So unlike pressure or temperature, work is not a property of a state, it's a property of the process connecting two states. But we do still have to evaluate that integral. You'll see four common shapes for these processes. The first, isochoric, constant volume, like a rigid container. It's drawn as a vertical line, so there's no area underneath a vertical line, so work is zero. Done. Zero work on the system, zero work for engineering students. The second, isobaric, constant pressure, a horizontal line. In this case, the area is just a rectangle. Work is equal to base times height. Third is polytropic, the general workhorse. Any process that follows the form PV to the n equals C, where n is the polytropic exponent and C is a constant. I'm not going to derive the whole thing. Hey, calculus is your friend, not mine. But amazingly, it does eventually simplify down to this easy formula that doesn't even have the constant in it. Though your problem statement probably won't give you both P2 and V2, so you'll have to use the constant to find either P2 or V2, whichever one you're missing. The fourth one is isothermal, a constant temperature. PV equals MRT, where MRT is constant. This is what happens when your polytropic process has n equals 1. And because you can't divide by 0, for an ideal gas only, we can substitute PV equals RT into the integral and you get a natural log. This isothermal case shows up constantly on the FE exam. One other keyword reminder, adiabatic, for no heat. That is a polytropic process with n equal K, where K is the specific heat ratio, which we'll meet later.
Another new variable? I'll wear my fanciest tie. Last time I forgot, and entropy never respected me again.
Here's the most relatable closed system in your life, a car engine cylinder. This is the model of a 4-stroke gasoline engine. Intake, the piston moves down, fresh air-fuel mixture flows in. Compression, piston up, volume drops, pressure spikes. The work during compression is negative. Work done on the gas. Power costs money. Then ignition. A big addition of heat followed by the power stroke. The piston gets pushed back down by the expanding hot gas. That work is positive, work done by the gas. This is what's actually turning the tires. Then last is the exhaust stroke. The piston goes back up, pushing out the burned gases. Remember the Rankine cycle for our power plant? This engine is following a different cycle, the Otto cycle. If I plot all 4 strokes on a PV diagram, they form a closed loop. Area under the top expansion process is positive work. Area under the compression process is negative work. The area enclosed equals net work of the cycle.
What about that random horizontal line down at the bottom?
Those are intake and exhaust processes. It's 2 lines right on top of each other. They cancel each other out. So that's it. The entire engine, 4 strokes, thousands of RPM, all the noise and fire, it boils down to an enclosed area on a PV plot. Step 1. Identify the process. Polytropic. PV to the n equals constant. Step 2. I need V2 and I don't have it directly, but I have everything else, so I use PV to the n equals constant, meaning PV to the n initial equals PV to the n final. So V2 is 0.1008 meters cubed. And this is compressed. Volume dropped to 1/4. So yes, that makes sense. Sanity check passed. Step 3, plug into the polytropic work equation. And I get work, negative 68.3, and negative, which makes sense. We compressed the gas, so work was done on the gas, not by the gas. If you got plus 68, you flipped a sign somewhere. Let's stitch boundary work back into the closed system energy balance from chapter 2. For most closed system problems in this course, the only work term is boundary work. So delta U equals Q minus boundary work. So a quick checklist for any closed system problem. 1. Calculate boundary work as area under the PV diagram curve. 2. Find delta U from tables, or coming up next, you can find it using specific heat. Step 3, solve for whatever's left. And then step 4, feed Serenity more snacks. Serenity, have you been using my tablet?
How dare you accuse me without any evidence?
All right. Well, don't ever say I don't follow procedures. Oh, and if you have multiple processes that form a closed loop, a cycle, then all of your changes in internal energies from each of the process have to all add up to 0, since you end up back where you started. So all of your delta U's for each individual process have to add to 0. Sometimes that last little trick is needed to find your last unknown. So that's it. That's the template for every problem in this chapter. Even step 4, feeding Serenity extra snacks. She assures me that step is not optional. For water and steam, we look up internal energy in the tables. But for ideal gases, air, nitrogen, oxygen, most textbooks have tables for these also, but there's another way. You can use specific heat. How much energy does it take to change the temperature of something by 1 degree? That is the definition of specific heat. There are 2 of them, CV, specific heat at constant volume, and CP, specific heat at constant pressure. Both have units of kilojoules per kilogram Kelvin. Now for an ideal gas, and this is the magical part, internal energy and enthalpy depend on temperature only, which means we get 2 clean equations. And warning, always use CV when finding internal energy. Always use CP when finding enthalpy. It doesn't matter whether your problem is constant volume or constant pressure. Think of these subscripts, V and P, as historical leftovers that don't really apply anymore. Are you finding U or H? That's all that matters. Finding U, CV, finding H, enthalpy, CP. So you're usually interested in CV, closed system, CP, open system. And good news, you only have to decide for gases. Liquids and solids, since they are incompressible, they don't have CV, only CP. Just one. So you'll never get them mixed up for liquids or solids.
Hey, Indy, guess why I've been having trouble getting a job?
Because you're lazy and irresponsible?
No, it's because cats are liquid, so I don't have a CV.
So 2 more relationships to relate terms you've already heard in this video. CP is equal to CV plus R. That's kind of interesting. gas constant appears here, but Cp is always bigger than Cv. Why? It's because when you heat a gas at constant pressure, some of your energy has to go into pushing the piston out. That's boundary work. At constant volume, all of the heat goes straight into raising temperature. So you need more energy per degree at constant pressure to account for this work that you're also doing. That ratio K, the specific heat ratio, for air, K is about 1.4. For monatomic gases like helium, 1.67. K shows up in adiabatic processes and compressible flow. This is why you'll see lots of homework problems in your textbooks using air in a polytropic process with N equal to 1.4. With N equal to K, this is an adiabatic process, no change in heat. It's one of the easiest cases to model, but it's not always this way. A few minutes ago, we did an example problem with N equal to 1.3. That was not adiabatic, so there would have been some heat gain or loss in that system that we just didn't calculate. So there wasn't just boundary work. Oh, and one morning, Cv and Cp actually drift slightly with temperature. Across a small delta T, you can treat them as constant. But if your temperature is changing by hundreds of degrees, then you can get a better estimate by averaging your initial and final specific heats. It's not perfect, but it's usually good enough. So how do you actually measure specific heat for a real substance? Calorimetry. Let's do a material identification experiment. I have a chunk of hot gray metal at a known mass. I'm going to drop it into a known mass of room temperature water inside this insulated foam cup. The water heats up, the metal cools down. They meet at some equilibrium temperature in the middle. No work is being done, and the cup is insulated, so Q across the boundary is 0. Energy is conserved inside the cup, so all of the heat lost by the metal equals all of the heat gained by the water. So mCp delta T for the metal equals mCp delta T for the water. Some call this equation mCp delta T the MCAT equation, since the delta looks like an A.
I approve of all cat-related memory aids.
So, since I know Cp for water, every term in that equation is known except for Cp of the mystery metal. Solve for it, and then check a materials property table to find the metal with the closest specific heat. And it looks like this is probably aluminum. And hey, there's an Al stamped right on the top of this cylinder. What a coincidence. And me, I thought his name was Al. No, cut that joke. It's not funny. Anyway, this is how every value in your textbook's specific heat tables originally got there. Tens of thousands of careful calorimeter measurements. At the exam style question, closed system, piston cylinder, air, low pressure, ideal gas assumption is good. So delta U is going to equal Q minus W. Find delta U, find W, and then we'll get Q. So step 1, boundary work. It's isobaric, so a horizontal constant pressure. So work is area of a rectangle, 10 kilojoules. So step 2, internal energy change. For an ideal gas, delta U will be mCv delta T. We'll find the mass using PIVMERT. So PV equals MRT. Rearrange M is PV over RT. 0.1161 kilograms. Step 4, find T2. We're at a constant pressure, volume doubles. So from the ideal gas law, V over T is equal to V over T at time 2. So if we double the volume, we double the temperature. T2 equals 600 degrees. So delta T, 300 degrees. So we plug in 0.1161 times 1.005 times 300. Wrong, it is a trap. The problem gave me CP, not CV. Remember, your professor is evil, unless you're in my class. I trick you because I care. I want you to learn. Other professors trick you because they are mean. Don't trust them. You have to use the relationship CV equals CP minus R. So 0.718 will be CV. So now plug that in, 25 kilojoules, and then solve Q equals delta U plus work. Q is 35 kilojoules B. Now, there is a humongous shortcut for this problem also, which we just haven't quite got to yet. But previewing what we'll do in the next chapter, which is solve for Q directly. For constant pressure specifically, there's a one-line move. At constant pressure, Q is m Cp delta T. The boundary work is already baked in to Cp. So 35 kilojoules, one line. That's it.
CAT equations are known for their efficiency.
And that is the secret of Cp. It's defined exactly so that at constant pressure, Q equals mCp delta T. Boundary work is included automatically. So constant pressure heating problems become one-liners. The same trick works for constant volume. A vertical line on a PV diagram with no area underneath, so work is 0. And delta U would then be Q equals mCv delta T. Also, just one line. Recognize the process, use the matching specific heat, skip half the algebra. That is the real speed weapon on the FE exam. So chapter 4, closed systems, 4 things to remember. Boundary work is area under the PV curve. It's path dependent, not a property. This one polytropic formula covers most processes. Specific heat lets you skip the tables for ideal gases. And last, the constant pressure shortcut Q equals mCp delta T. It works for both closed systems and, as you'll see in the next chapter, also open systems. All right, enough engines. I am a nuclear engineer, and this is a power plant class. Next chapter, we open the system back up. Mass crosses the boundary. Turbines, pumps, nozzles, heat exchangers, every component in the Rankine cycle we promised you in chapter 1. Welcome to Jurassic Park. I mean, open systems. All right, if you want to keep your dinosaurs in a well-functioning amusement park, closed systems are great. Mass stays put, and only energy crosses the boundary. But open up the floodgates, literally, and you get open systems. We usually call these control volumes. Same thing, open system and control volume, same thing. Mass flows in, mass flows out. We're finally analyzing the real components of the Rankine cycle. Turbines, pumps, nozzles, heat exchangers, the actual machines that make a power plant work. The energy balance still applies, but we need to add one new conservation law first.
I'm not fat. I'm conserving mass.
If mass is crossing the boundary, we need to track it. Mass is conserved. It doesn't just appear or disappear. But just like energy in chapter 2, we want this in rate form. So we use mass flow rate, m dot, units of kilograms per second. 3 ways to write it. Density times area of the pipe times velocity, or since specific volume is just the inverse of density, you can do area times velocity divided by specific volume. Use whichever of these forms matches the givens in your problem. And a quick warning of capital V. Capital V usually means volume. Lowercase v usually means specific volume. What the heck was that? But then there's velocity, which most textbooks also call capital V. Could be capital or lowercase. Understand the meaning of your equation. Don't just read the letter, double check your units. Because V, there's a lot of different Vs. So this is the mass rate balance for a control volume. In English, the rate of mass accumulating inside a box equals what flows in minus what flows out. If TA Serenity eats one churu and doesn't poop it out, her mass increases.
You do not want to be near the litter box when it's m dot out time.
For steady state, which is the vast majority of your problems, mass inside the control volume isn't changing. The left side is 0, so box this equation. Now for a single inlet, single outlet, like a pipe, it's even simpler. Just mass in equals mass out. That's mass conservation. So now back to energy.
Goodbye, Serenity. Energy is my domain.
When mass crosses a boundary, it carries energy with it, internal, kinetic, and potential. But it also has to push itself through the pipe, doing flow work. Remember chapter 3. So that's exactly why we invented enthalpy. H equals U plus PV. Closed systems get U, open systems get H. Do not mix those up. The full energy balance for a control volume is a beast. Heat, work, enthalpy, kinetic energy, potential energy. Let's tame it. If you're in steady state, then dE dt, the rate of energy change, is 0. For a common single inlet, single outlet case, mass flow rates are also equal, so you can factor out the m dot. So box this equation. This is the steady flow energy equation, SFEE. It's the workhorse of chapter 5. For most components, kinetic and potential energy changes are negligible, so your SFEE collapses even further. You'll use this version 90% of the time.
60% of the time, it works every time. I learned that from a cat-based cologne, so you know it's accurate.
Now here is where the SFEE gets friendly. Each Rankine cycle component has its own set of simplifications. Learn the pattern and the math becomes fast. Turbines and compressors. These move fluid so fast through the blades that heat transfer doesn't have time to happen. So they are adiabatic. Q dot equals 0. Kinetic and potential energy changes are small compared to work, so you can also drop them. What's left is work is just m dot change in enthalpy. For a turbine, H1 is bigger than H2. So W dot is positive, work out of the system. The power plant sign convention from chapter 2. For a pump or compressor, H2 is bigger than H1. W dot comes out negative. That's work into the system. Same equation, the signs sort themselves out. Now don't memorize these individual component equations. Just use the main energy balance equation every time. And if you understand how these components work, you'll be able to just cross off the terms you don't need, and the one equation will work for every piece of machinery, so it's way less to remember. A nozzle accelerates a fluid by squeezing it into a smaller area. A diffuser does the opposite. There's no shaft, no moving pieces at all, so no work. W dot equals 0. It's typically adiabatic, so Q dot is 0 too. Little or no change in height, so what's left is essentially converting enthalpy to velocity, or the other way around. Now warning, every student messes this up the first time, except for you. You're awesome. You're going to nail it. If your velocity is meters per second, then v squared gives you joules. But enthalpy is usually in kilojoules. You'll need to divide your v squared over 2 term by 1,000 to convert it also to kilojoules. This is the one time kinetic energy actually matters in this course. The whole point of a nozzle is to trade enthalpy for speed.
At snack time, I trade dignity for speed.
Heat exchangers. 2 fluids passing each other, exchanging heat through a wall. There's no shaft, so W dot equals 0. Kinetic energy and potential energy terms are also negligible. Now, you have a choice, and pick wisely. Professors love this trap. They are evil. Not me, just all of the rest of us. Draw a control volume around just one fluid stream, then Q dot equals M dot delta H for that stream only. Or draw your control volume around the whole heat exchanger, and now Q dot equals 0, because all the heat stays inside the box. Then, in that case, the heat lost by one fluid equals the heat gained by the other fluid. So same idea as the calorimetry demo from the last chapter. Same energy bookkeeping, just different equipment.
If I draw the control volume around the entire kitchen, I can't get in trouble for stealing snacks, since they're all still in the kitchen after I eat them.
I promised you turbines in chapter 1, so here is a model of a turbine. This is a multi-stage steam turbine. Real power plant turbines look more or less like this, only 50 feet long and cost millions of dollars and are made of metal instead of plastic. So exactly the same. It's got 3 rotor stages with 2 stators in between. So why multiple stages? Because no single set of blades can efficiently extract all of the energy from high pressure steam. Each stage drops the pressure a little, it extracts some work, and then hands the fluid to the next stage, where you have stationary blades to redirect the steam at the perfect angle to hit the next set of moving blades. I'm putting energy in as airflow. Each stage takes a bite, and by the time the air exits, most of the pressure and kinetic energy is gone, converted to shaft rotation. In your energy balance equation, the turbine is a single black box. H1 in, H2 out, and work comes out the side. But this is what's happening inside. There's multiple stages of coordinated energy extraction.
I'm still mad that Duke Energy rejected my cat-powered turbine power plant design.
All right, FE exam style problem. We've got turbine, constant volume. We'll assume steady state. Start with the SFEE. We're adiabatic, so Q dot is 0. It's a turbine, so we'll ignore kinetic and potential energy. So what's left? W dot is M dot change in enthalpy. So 2 enthalpy lookups in the steam tables. State 1 we're given is 5 megapascals and 500 degrees Celsius. Normally, I would check the saturated table first, but if state 2 is saturated vapor, then state 1 is going to have even more energy. So state 1 is probably a superheated vapor. So I check there first, find the 5 megapascal mini table, look for 500 degrees Celsius, and boom, there it is, 3434.7. State 2 is a saturated vapor at 50 kilopascals, so the quality is 1 since it's a saturated vapor. I go to the saturated pressure table, 50 kilopascals row, and get Hg column for the saturated gas, 2645.2. Remember, to look up values in the steam tables, you always need 2 pieces of information. At state 1, I had pressure and temperature. At state 2, I had pressure and saturated vapor, meaning quality equals 1 was my second piece of information. So now plug everything in and answer C, 7,900 kilowatts. So notice the algorithm. Identify the component, apply the right simplification, 2 table lookups, plug in. That's the recipe for every steady state open system problem in this chapter. Get fast in this exact workflow. You'll see it probably 5 times in the thermo section on the FE exam. Super common. Now, almost everything in this chapter is steady state, but there are a few classic problems where it isn't. Filling a propane tank, or discharging a pressure vessel, charging an HVAC accumulator. Mass inside the control volume is changing with time for these cases. You're filling something. The dm/dt term that we've been zeroing out, the change in mass in the control volume, it's alive now. For these, we need to integrate the rate equations from time 1 to time 2. Let's show how this can simplify as an example problem. So unsteady flow. The tank starts empty, M1 equals 0. Rigid means no work. Insulated means no heat. There's no exit, so M out is 0. So our mass balance, M2 equals mass in. So the energy balance, Q is 0, W is 0. There's no exit flow. And initial energy is 0 because the tank started empty. So M2U2 is mass in times H in. So since M2 is equal to mass in, the mass cancels, and we're just left with final internal energy equals enthalpy that entered. That's the magic move for these problems. The final internal energy in the closed system tank equals the enthalpy that passed through the control volume border in the supply line to enter the system. So we look up enthalpy in. If the supply was 1 megapascal, 300 degrees Celsius, saturation at 1 megapascal is 179. So this is superheated. So we go to the superheated table, 1 megapascal, 300 degrees Celsius, H in 3051.6. So U2, final internal energy, 3051.6. To find temperature 2, our final state, pressure 2 is 1 megapascal, U2 is 3051.6. So we go back to the 1 megapascal mini table. We scan the U column, internal energy, for 3051.6. It falls in between 400C and 500C. So we interpolate. Left fraction is U, right fraction is T. And notice the placement of all 4 terms on both sides. Each internal energy corresponds to the corresponding temperature in the same place on the other fraction. So pop quiz, if you fill a tank with 300 degrees Celsius steam, what temperature will it be? 456 degrees, duh. Well, what the heck is even that? The final temperature is higher than the 300 degree supply line because as the steam pushes its way into the tank, It does flow work on the gas already inside. That flow work becomes internal energy, which increases temperature. This is a classic counterintuitive result. It's also a favorite of all those evil professors who aren't me.
You never let me catch the red dot. If that's not evil, I don't know what is.
Chapter 5, Open Systems or Control Volumes. 2 names, same thing. 4 things to take with you. Mass is conserved, just like energy. Mass in equals mass out, unless there is accumulation, filling or emptying a tank. 2, use enthalpy, not internal energy. In open systems, flow work is already baked in to enthalpy. 3, each component, turbine, heat exchanger, nozzle, they all have a simplification pattern, but don't memorize 50 different equations for every different possible machine. If you understand what the machine does and how it works, you only need to know the energy balance, and then you just cross off all the terms you don't need. But be extra careful with heat exchangers. Choose your control volume wisely. Sometimes you want to draw it only around one of the fluid flows. Sometimes you want to draw it around both. And finally, for unsteady tank filling problems, U final equals enthalpy supplied. Easy game. Next chapter, the second law of thermodynamics, which is also, you don't talk about thermodynamics.
Stop making Fight Club references. That movie is 27 years old.
Fine. The second law of thermodynamics governs thermal efficiency. And it introduces entropy. Entropy is the thing that everybody pretends to understand, but they actually don't. So good luck with that.
See? Evil.
All right, your TA Indiana's back because he's all about energy. The first law is about quantity. Energy is conserved. But the second law is about quality and direction, which is way more complicated. Yay! According to the first law of thermodynamics, a cup of hot coffee sitting on your desk could spontaneously absorb heat from the cooler room and boil itself. No energy would be created or destroyed in that process, but it never happens. Processes have a natural direction. To understand why, we need the heavyweight anchor of mechanical engineering, the second law of thermodynamics. But before we hit the law itself, we need 2 definitions. First, a thermal energy reservoir. This is a hypothetical body with a massive thermal energy capacity that can absorb or reject an infinite amount of heat without changing temperature. Think of the atmosphere or the ocean. If a reservoir supplies heat, we call it a source. If it absorbs heat, we call it a sink. Second, a heat engine. These are cyclic devices designed to convert heat into work. Every single heat engine on Earth does 4 things. It receives heat from a high temperature source. It converts part of that heat into work, usually by a spinning shaft. It rejects the remaining waste heat to a low temperature sink. And then the cycle repeats. A power plant Rankine cycle, that is a heat engine. An Otto cycle for the engine in your internal combustion car, another heat engine. You pay for QH worth of fuel, and your power plant sells W net worth of electricity, or your car converts W net into miles. QL is exhaust. It's necessary by physics.
Am I a heat engine? Step 1, cry for food. Step 2, convert food into naps. Step 3, reject hairballs onto the carpet. Step 4, repeat.
That will never get through peer review.
To measure how well a heat engine works, we use thermal efficiency. Like we said in Chapter 2, efficiency is always what you want, divided what you have to pay for it. For a heat engine, you want net work output. You pay for the heat going in. So, what's the maximum possible efficiency? It's not 100%. But we need some theory first before we can calculate it. We need the second law of thermodynamics. Now, there are two classic statements of the second law.
Hold up. 2 classic statements? How many statements of the second law of thermodynamics are there?
Well, Wikipedia lists at least a dozen.
I want one. Don't move. I'll be right back.
Well, hurry up. I'm not waiting for you. Well, so one of the reasons the second law is so hard for students is because there's no single concise description of it. There's dozens of different versions that really all say the same thing, but just in different ways. But there's one that's the most popular, the Kelvin-Planck statement. In English, no engine, no matter how cleverly designed, can take heat from a single hot source and convert 100% of it to work. There must always be some heat rejected to a cold sink. Hot things don't give up their energy for no reason. Energy flows from hot to cold, and your heat engine can be a tax collector, pulling out energy along the way. But a 100% efficient heat engine is physically impossible.
Oh, since I'm 100% efficient in everything I do, that means I'm not a heat engine. Glad we cleared that up.
Let's make this abstract law completely undeniable. This is a classic steam engine. It's a living, breathing heat engine. Right here, these burning fuel pellets act as our high temperature source, dumping heat into the boiler. The water absorbs that energy, boils into high pressure steam, and expands inside the cylinder, pushing the piston to do work, W net, which spins the heavy flywheel. But look here at the exhaust valve. See that steam escaping? That is QL. That is the mandatory tax required by the second law. The engine cannot extract work unless that steam expands out into the cooler room, which acts as our low temperature sink. If I plug that exhaust hole completely, the piston locks up instantly and the wheel stops turning, which I'm not going to do because I don't want to break anything. But point stands. No heat rejection, no work. That's Kelvin-Planck. Don't like Kelvin-Planck? Don't worry, I got another one. The Clausius statement. Drop an ice cube in your coffee. The ice cube melts and the coffee cools. Heat flowed from hot to cold naturally. No help is needed. Now, imagine the reverse. The ice cube gets colder while the coffee gets hotter, spontaneously. That would not violate the conservation of energy, but that never happens. What about a refrigerator, you ask? They pull heat from the cold inside and dump it into the hot kitchen outside. How? Well, you plug it in. The Clausius statement says, heat won't flow uphill on its own, but with external work input, it can.
My refrigerator won't work unless I plug it in. And I won't work before my morning churu.
A refrigerator and a heat pump are the same device. Same components, same cycle. The only difference is which reservoir you care about. A refrigerator, energy flows from cold to hot in order to make the cold space colder. The useful output is QL. A heat pump, energy flows from cold to hot in order to make the hot space hotter. The useful output is QH. The first law for a cycle is the same as before. QH is equal to QL plus net work in. But we don't measure efficiency for refrigerators or heat pumps. Why? Because the ratio comes out greater than 1. And engineers got tired of explaining to non-engineers that 400% efficiency is actually okay in this case. So we renamed it coefficient of performance. And there's a clean relationship between the two. Coefficient of performance of a heat pump is the coefficient of performance of a refrigerator plus 1. The extra plus 1 is because every joule of work you put in eventually gets dumped as heat into the hot reservoir. It's like a buy one, get one deal. You pay to pump the cold air, and you get the compressor's waste heat absolutely free.
I use that exact same plus 1 formula for treats. The coefficient of a perfect meal is always the number of snacks I just ate, plus 1 more.
Heat pumps are low-key amazing at heating buildings. Way better than an electric resistance heater. Because heat pumps steal energy from outside air for free. And your only cost is the compressor. All right, FE exam style problem. Step 1, find the work using first law on a cycle. QH equals QL plus work. So 200 kilojoules. Step 2, coefficient of performance. This is what you want divided by what you have to pay in order to get it. You want the cold space to be colder, so the numerator is QL. You pay for the work input. Gives a coefficient of performance of 3. Answer B. For every 1 joule of electricity you pay for, 3 joules of heat are pulled from the refrigerator. Not too shabby. Indy, you're not going to come back for this part? He talks about perpetual motion machines all the time. Engineers, inventors, and your TA Indiana over there, they have spent centuries trying to break the first and second laws. They have all failed. They will continue to fail. The US Patent Office has a standing policy. They will not even review a perpetual motion machine application without a working prototype. And they will never get one. Their failures come in 2 different flavors. A PMM of the first kind violates the first law. It creates energy from nothing. The output is greater than the input. These are sometimes branded as free energy devices. A PMM of the second kind violates the second law. It doesn't create energy, but it converts heat to work with 100% efficiency. It's an engine with no exhaust. Or it moves heat uphill from cold to hot with no work input. Both kinds are impossible. Do not fund your TA Indiana's Kickstarter. We already determined the second law sets legal limits for efficiency. Every engine you'll ever analyze falls into one of 3 buckets. Reversible, the theoretical best, frictionless, perfect. It doesn't actually exist anywhere in the universe, but it's our ceiling. You could undo it completely without leaving any trace on the system or surroundings. Irreversible, this is the real world. Every actual engine, it has losses, friction, mixing, things that can't be undone.
Like saying, I love you. You can't unsay it. Once it's out there, it's out there.
And last, impossible. Efficiency exceeding the reversible maximum, or 100% conversion of heat to work. It violates the second law. It does not exist. It can't exist. Reversible, irreversible, impossible. 3 kinds. If you solve a problem and you calculate an efficiency above the reversible maximum, you made a math error. That is not your professor's fault. Probably. Maybe. Some professors are lazy and don't actually check the problems they assign, so also that could have happened. So what makes a process irreversible? Friction is the big one. Unrestrained expansion of a gas, heat transfer across a non-zero temperature difference, mixing of different fluids, current flowing through an electrical resistor, which we call I²R losses, or chemical reactions. If any of these are present, and they always are, your process is irreversible. Real processes are always irreversible. The reversible process is the asymptote that can never quite be reached.
My nap is reversible. I lie down. I stand up. No trace left behind.
Except for the mountain of cat hair that she leaves behind. So, irreversibility confirmed. In 1824, a French engineer named Sadi Carnot asked the question, what does the most efficient possible heat engine look like? His answer is the Carnot cycle. 4 reversible processes between 2 temperature reservoirs. Isothermal expansion at the hot temperature. That's heat added. Then adiabatic expansion. No heat, just a temperature drop down to the cold temperature. Then isothermal compression at the cold temperature, where QL heat is rejected. Lastly, adiabatic compression. No heat, but temperature climbs back up to the hot temperature. If work is area under the curve on a PV diagram, then I fully admit this diagram looks like a nightmare to integrate. But don't panic. In the next chapter, we will introduce the TS diagram, temperature entropy. And there, the Carnot cycle is a beautiful, clean rectangle. So stick with me until then. It's coming. But for now, the main takeaway is that all 4 steps are reversible. Therefore, it's impossible to actually build this engine. But the math is beautiful, and it sets the efficiency ceiling for everything. Box this one. That's the maximum thermal efficiency of any heat engine operating between 2 temperature reservoirs. 2 non-negotiable details. The temperature must be absolute. Kelvin or Rankine, not Celsius or Fahrenheit. Get this wrong, and your answer turns to garbage, and your professor will look at you with deep sadness. An important historical trivia, Lord Kelvin actually used the Carnot heat engine to create the Kelvin temperature scale. Kelvin temperatures were literally invented for this. Don't forget to use them. And second, the design lesson. A bigger temperature gap means a bigger maximum efficiency. So engineers either crank T-hot up with better materials or supercritical steam, higher furnace temperatures, or drop T low down like a deep ocean condenser or colder cooling water or drawing a vacuum, right? Both T-hot increases or T-low decreases both increase your efficiency ceiling higher. Now, this same form of efficiency can also be applied to refrigerators and heat pumps for the maximum possible coefficient of performance with two sources and sinks. So these equations should look familiar because we've seen them before. But now we're just using them with temperature. Last time you saw them, those T's were Q's for heat. So you use temperature to find the theoretical maximum. You use heat when you're calculating the actual performance of your real system. The Carnot cycle is theoretical. You can't actually reach it. But the Stirling cycle is its real-world cousin. 2 isothermal processes plus 2 constant volume processes. It's the closest practical thing we have to a Carnot engine. And look at that. A burner heats the bottom. That's the hot reservoir. The room air on the top, that's the cold reservoir. The temperature difference drives the cycle. Pistons move air back and forth between the hot and cold ends. Work comes out of the flywheel, and the flywheel spins a small generator that lights up the LEDs. There's no combustion inside the engine. There's no fuel injection, no explosions, just work from a temperature difference. Stirling engines powered some early refrigerators. They fly on deep space NASA probes for thermal management, and they're studied today for low-grade waste heat recovery. They're efficient, quiet, and elegantly simple. But they still never quite reach Carnot.
Where's Indiana? I'm doing all the physics and all the comedy. He better be picking up snacks.
So next example problem, step 1, find the actual efficiency. So for this we use Q and we get 50%. Step 2, find the Carnot reversible maximum possible efficiency for these temperatures, which is 62.5%, and compare them. Since 50% is less than 62.5%, this engine is operating below the reversible ceiling. That's allowed. That's good. That's the entire real normal world. So answer is B, irreversible. If the actual had been exactly 62.5, then it would have been reversible. If it had been 70%, that would be impossible. So congratulations, 70%, you've broken the laws of physics, and possibly your homework grade. So this problem type appears in some form on nearly every FE exam. 3 steps: calculate the actual, calculate the Carnot, and compare. All right, next, a little bit bigger practice problem. We're building up to it. So a heat pump problem, we want to keep the hot side hot. So the useful output is QH. Step 1, convert temperatures to absolute. We are Kelvin only. Step 2, use the reversible coefficient of performance to find out the best possible case. 14.75 is our best coefficient of performance, maximum possible. That is huge. For every 1 kilowatt of electricity you use, you deliver 14.75 kilowatts of heat into the house. But this is the reversible ceiling. Nobody actually gets quite to that level. Real residential heat pumps come in around coefficient performance of 3 or 4. That's still way better than an electric resistance heater, which is permanently stuck at a coefficient of performance of 1. All right, step 3, find the required work input. So the house is losing heat at 75,000 kilojoules per hour. So the heat pump must deliver heat at the same rate to hold temperature steady. So Q hot, 75,000. Work in, right, just rearrange, about 5,000 kilojoules per hour. Convert that to kilowatts by converting the hours to seconds, 1.41 kilowatts. So the minimum power to heat this house reversibly is about 1.4 kilowatts. A real heat pump with coefficient of performance of 4 would draw about 5.2 kilowatts. An electric resistance heater would draw 20.8 kilowatts for the same heat delivery. And now you know why heat pumps are taking over residential heating.
I am a heat pump. I extract heat from sunbeams and deliver it to laps. Coefficient of performance? Infinite, since I require 0 electricity.
But you require constant snacks.
That's biofuel, not electricity. Totally different.
Chapter 6, the second law of thermodynamics, 4 things to take with you. 1, heat engines need a temperature gap. No cold reservoir, no work. That's Kelvin-Planck. 2, heat flows downhill on its own, from hot to cold. But to go uphill from cold to hot, that costs work. That's Clausius. That's the entire reason refrigerators and heat pumps exist. Number 3, engines use efficiency. Refrigerators and heat pumps use coefficient of performance. But they're all still useful output divided by paid input. And 4th, Carnot efficiency is the absolute ceiling for heat engine between 2 temperatures. But when calculating it, use absolute temperatures only. Honor Lord Kelvin's legacy.
I'm back, and I've got the best second law statement. While it's impossible to achieve Carnot efficiency, it's even more impossible to exceed it.
It's grammatically nonsense. I hate it.
I love it. It helps me remember the difference between impossible because of friction and impossible because of math and physics. The Carnot ceiling is less than 100% because of math and physics. Real engines operate less than the reversible Carnot ceiling because of friction and vibration, irreversibilities. That's what TA Indiana's statement says. So to me, it's perfect. Good job, buddy. Your statement's perfect. Students love it. But speaking of irreversibilities, these are also why we need the next chapter, because to actually quantify the irreversibility, to put a single number on how far we are from perfection, we need a new property. The most feared and misunderstood property in all of thermodynamics. Entropy. All right, TA Indiana, real quick. Before entropy, there's a third law of thermodynamics. It says that entropy of a perfect crystal at absolute 0 is exactly 0. That's the whole law. We need a reference point for entropy, and the third law hands it to us for free. So mention it on a test, get the point, move on.
That was a lot easier than the second law.
And we're not even done with the second law yet. Here's the real reason everybody struggles with entropy. The second law was complicated because there's a million different definitions, but at least they all agreed with each other. There are different ways to say the same thing. But for entropy, there are actually 2 accepted definitions, and they do not fully agree with each other. Whoa, careful. So the classical definition based on the experimental work of Clausius for a reversible process, change in entropy is a ratio of heat transferred divided by the temperature of the system. If you extend the implications of this work, you get other formulations of the second law of thermodynamics, including entropy of an isolated system never decreases. That's a hard law, no exceptions, ever. And guess what? If we draw our box around the entire universe, that is an isolated system. So the entropy of the universe never decreases. That's the second law of thermodynamics. But the second definition, the statistical definition from Boltzmann, entropy is a count of all the microscopic arrangements that could correspond to a macroscopic observation. More possible rearrangements, higher entropy. So your TA Serenity, freshly groomed with her fur still on her body. That's a relatively low entropy state. There are far fewer ways for her hair to be arranged on her body than scattered all over the house. Spread the same hair across the couch, my shirt, in my food. There's way more possible arrangements, therefore higher entropy. But here's the key. In this framework, entropy decreasing spontaneously isn't actually illegal. All the cat hair all over my clothes and furniture, it could spontaneously still end up back on Serenity all on its own. Boltzmann just says it's so astronomically unlikely we treat it as impossible. Those two definitions don't say the same thing. Clausius says entropy decreasing is impossible. Boltzmann says astronomically improbable. For all the air in the room to spontaneously rush to one corner for no reason, Clausius says this can't happen. Boltzmann says it could happen. It just won't. Physicists and philosophers have been arguing about how to reconcile this discrepancy for over 100 years. There is no consensus yet. So, if you've always felt like you almost understood entropy, but not quite, that's not you. The definition itself is scientifically unsettled at its very foundation. Now, for me, I love poker. I love probability, but I do not like the Boltzmann interpretation of entropy. I'm a Clausius man. Give me rules and order. Because we're engineers. We build real things in the real world. You don't need a full microscopic theoretical framework to use entropy on the macroscopic level. Our great-grandparents already did all the math for us. We just look up entropy in a table. The steam tables we've been using for the past few chapters, entropy is in those. It's S. It's those last three columns we've been ignoring until now. Entropy is complicated, but it's just another property. So look it up in the table, just like every other property. And definitionally, that's everything you need to know to pass your thermo course and pass the FE exam and call out any know-it-all classmates or coworkers. So we'll leave the fundamental interpretation to the physicists and philosophers. They can have it. In chapter 3, we drew the PV diagram, pressure, volume. Now meet its cousin, the TS diagram, temperature on the vertical, entropy on the horizontal. Same saturation dome, same left side compressed liquid, right side superheated vapor, underneath the dome, two-phase mixture. Why do engineers love TS diagrams? Two reasons. One, The area under the curve on a TS plot equals heat transfer, Q. Just like area under a PV diagram was work. So T times ds, that's heat. And 2, remember how in the last chapter I said the Carnot cycle was going to clean up perfectly? Well, here it is.
Now we're talking. Even I could integrate this.
So 2 horizontal lines at T hot and T cold, the isothermal heat transfer steps, and then 2 vertical lines are the adiabatic reversible steps. A perfect rectangle, area inside equals net work. Area under the top is QH. Beautiful, easy. A vertical line on the TS diagram means constant entropy. We call that isentropic. An isentropic process is one where entropy doesn't change, delta S equals 0. So for that to happen, 2 conditions must be true. Adiabatic, so no heat transfer, Q equals 0, and reversible, no friction, no mixing, no irreversibilities. Adiabatic plus reversible equals isentropic. So let's see an isentropic process in an example problem. All right, it's isentropic, so S2 will equal S1. Now, at state 1, we're given 4 megapascals and 400 degrees Celsius. Now, saturation at 4 megapascals is 250.35 degrees Celsius. We are hotter than that, so it must be superheated. So I go to the 4 megapascal mini table, 400 degrees Celsius row, get entropy 1, 6.77. Now, at state 2, we're 50 kilopascals and entropy of 6.77. So I check the saturated pressure table at 50 kilopascals, see that SF 1.09, SG 7.59. Since our entropy 6.77 falls in between them, state 2 is a wet 2-phase mixture. So we've identified the phase. So I set up the quality fraction, same technique as chapter 3, just with entropy instead of enthalpy. I see that the quality is 0.87, 87%, so the closest answer, B. That's actually the workhorse pattern for the Rankine cycle. The turbine exit from your power plant is almost always a wet mixture, and isentropic analysis with S2 equal to S1 is how you find quality. So lock this pattern in. But real-world machines aren't isentropic. Turbines, pumps, compressors, nozzles, if we insulate them or water passes through them really quickly, we are approximately adiabatic, but they aren't reversible. Real components fall short, and we measure how short with isentropic efficiency.
My isentropic efficiency at locating snacks is exactly 1.0. I am the Carnot cat.
So let's look at our Rankine cycle power plant on a TS diagram. For a turbine, you want big work output. So the isentropic case, a vertical line gives you the maximum. Reality gives you this line that goes slightly to the right. H4 actual will be slightly higher than H4 isentropic, meaning we did not get as much energy out of the system as theoretically possible. So actual work over ideal work. Real turbines have isentropic efficiency around 85 to 90%. For a pump or compressor, you want minimum work input. The isentropic case is still a vertical line. The real-world case also ends up to the right. So H2 actual is larger than H2 isentropic. But the efficiency fraction is upside down compared to the turbine version It's to ensure that the larger term is in the denominator. This time, ideal work over actual work. So the trick on these problems is solve the isentropic case first, and then if you know entropy, say at points 1 and 3, then you know S2 entropic and S4 entropic. They're the same as S1 and S3. Let's actually measure the gap between theory and reality. So this is a heat engine cycle. Air is sealed inside the small cylinder. It's connected to a piston that lifts a 200-gram mass. From 1 to 2, we add mass. So we are now at a lower volume and a slightly higher pressure. Next, from 2 to 3, we're going to switch from the cold over to the hot. You'll see volume increases, but pressure stays basically the same. Now, from state 3 to state 4, we're going to remove the mass. Which is going to be a slight increase in volume and a decrease in pressure. And then to complete the cycle, back to stage 1, go back to the cold bath. Now you can see pressure basically stayed the same, but volume decreased. And that is a heat engine. The area enclosed is equal to net work done, exactly like the Otto cycle from chapter 4. We can measure it. So we can also measure QH going in from the hot water. If you divide them, you get the actual efficiency. Then we can compute the Carnot efficiency just using the 2 bath temperatures. Carnot efficiency is the maximum possible. It will always be higher than the real-world value, always. The gap between those two numbers, that's irreversibility. That's entropy generation. Friction in the piston, heat transfer across the finite temperature difference, the gas not having time to fully equilibrate. I don't think any of those was correct. But every real cycle has irreversibilities.
Aw, this engine is sad because it isn't Carnot.
Every engine on Earth is sad because it's not Carnot. Welcome to engineering. For steam and refrigerants, just look up S in the table. Same workflow as for U and H. Now, for an ideal gas, we have 2 formulas. Same logic as specific heat, CV and CP in chapter 4. Just pick whichever one matches the information you have. So temperature in Kelvin, always, and natural logs, not log base 10. So use the first equation if you have temperatures and specific volumes. Use the second if you have temperatures and pressures. Both give the same answer. If you have all 3, use whichever one you want. They'll both give you exactly the same answer. For an isentropic ideal gas, where delta S equals 0, the second equation simplifies into what's called isentropic relations, where K is the specific heat ratio from chapter 4. So this is your fast tool for isentropic compression and expansion of air.
Ideal means perfect. Gas means fart. Whenever your engineering professor says ideal gas, pretend he's describing the perfect fart. Class will never be the same again.
So just like we had energy balances in chapters 2 and 5, there's an entropy balance for any system. Same accounting structure with one critical addition. So for a control volume in rate form, entropy accumulates in the CV due to heat crossing the boundary, due to mass carrying it in, mass carrying it out, and irreversibilities, which generate it internally. The term S.gen is total entropy generation rate caused by the irreversibilities like friction. And here is the golden rule of the second law. S.gen can never be negative. If S.gen is greater than 0, the process is irreversible and real. If S.gen is equal to 0, the process is completely reversible and ideal. If your calculator spits out an S.gen that is less than 0, you made a math error or invented a perpetual motion machine. Probably the first one.
My patience around the food bowl has 0 entropy generation. Therefore, my hunger is reversible. Feed me.
Homework problem. Entropy generation. Step 1, define the system. It's an open, steady flow compressor. So set up the rate form of the entropy balance. Step 2, apply the key adjectives from the problem statement. Steady state means that the accumulation term will be 0. The problem also says insulated, which means Q dot will be 0. I can divide the entire equation by mass flow rate and switch to S2 minus S1 since we subtract it to the other side, and we get our per unit mass generation. So step 3, use the ideal gas entropy equation since we're dealing with air. Step 4, substitute the given numbers into the equation. Step 5, evaluate the natural logarithms, being careful because there's fractions and parentheses. Boom. And the final value is positive, meaning the compressor is entirely possible in the real world and includes some irreversibilities. If the exit temperature had been lower, our entropy generation would have dropped below 0, which would alert us immediately to an impossible design.
I keep checking my entropy. It's still going up. That's good, right?
Indy, this is a thermometer. Do you have to go to the vet? Chapter 7, Entropy. 4 things to take with you. 1, the third law of thermodynamics. It just sets a baseline of entropy equals 0 for a crystal at absolute 0 temperature. As far as problem solving goes, it's not really relevant. At least not like the first and second laws. Those get used all the time. Second, look up S in the same steam tables you've been using all semester for water, but use equations to find S for ideal gases. Third, isentropic means adiabatic plus reversible. Set S2 equals S1. Solve for the ideal case, then apply isentropic efficiency for real components. And number 4, entropy generation is never negative. S.gen is greater than or equal to 0. It's the second law in math form. Negative S.gen means you made a mistake. So I have a comment challenge for you. Leave a comment down below with what thermodynamics terminology would best describe your professor. Example, Carnot. They are theoretically perfect, but impossible to find in the real world. Or isochoric. Does no work. I know some professors like that. So maybe superheated. They're full of positive energy. So be creative. I can't wait to read your comments. This is gonna be fun. Try not to be too mean, but it's okay to be a little mean, as long as it's in the spirit of good fun. All right, TA Serenity, it's final boss time. The Rankine cycle, going back to the power plant.
I too am ready for the final boss. The final boss of the trait factory.
We started this video with the Rankine cycle. You looked at it, you nodded politely, you had no idea what any of it meant. Pump, boiler, turbine, condenser, 4 arrows in a loop. Cute. Now that TA Indiana's joined us, now we've got the full toolbox to actually understand it all. So it's time to actually analyze the machine that powers most of human civilization.
I got this.
So 4 components, 4 control volumes, 4 applications of the steady flow energy equation. So each one you have actually done before, we're just stringing them together now. So state 1, a saturated liquid at the bottom left of the dome. Pump from 1 to 2. It compresses cold liquid water to higher pressure. This is adiabatic. Kinetic energy and potential energy are negligible. The process line is straight up if the pump is isentropic, 100% efficient. Otherwise, it slants slightly to the right, which increases entropy. The line is really short because liquid water is nearly incompressible, so temperature hardly changes as the pump increases pressure. But also, since water is essentially incompressible, there's a shortcut equation. It's just specific volume times pressure rise, usually only a few kilojoules per kilogram. Compared to everything else in a power plant, pumps are cheap. Now the boiler, from state 2 to state 3. Again, coal, nuclear, anything. It adds heat to convert high pressure liquid into high pressure superheated vapor. Temperature and entropy both go way up. Temperature curves upwards in the liquid and gas region, but under the saturation dome is always horizontal. Temperatures don't change during boiling. There's no work in the boiler, so this equation is just Q dot in. This is where you pay for your fuel. This is the biggest number in the cycle. Next, the turbine, from 3 to 4. Big spinning blades, multiple stages. The steam expands, drops pressure, and does work. It's adiabatic, and we can usually ignore kinetic and potential energy. Now, the line would be straight down if it were isentropic, 100% efficient turbine. Of course, that's impossible in the real world, so this line slants slightly to the right. Entropy has to increase. State 4 should normally be a liquid-gas two-phase mixture underneath the saturation curve, so some condensation happens inside the turbine. And this is the moneymaker. It's the whole point of building the power plant. The turbine is connected to the generator, which produces electricity. So last, condenser from state 4 back to state 1, a heat exchanger. It rejects waste heat out to the environment. There's no work. The horizontal line back to state 1 since temperature doesn't change during condensation. Now, Q dot out is required by the second law. You cannot avoid it. This can never be 0.
Hey, ho ho, the second law has got to go.
4 equations, 4 enthalpy differences. That's how the electricity is produced that charges your cell phone. FE exam problem, information overload.
I'm out. I surrender. Bury me in the litter box. That's too many numbers.
Amateur. When they put the whole buffet in front of you, you don't eat the salad. You locate the premium salmon pâté and ignore the rest.
Read carefully. The question asks for heat in the boiler. The boiler is just states 2 to 3. So we only need 2 numbers, H2 and H3, plus mass flow rate. Ignore everything else. It's just there to distract you and slow you down. The FE exam is full of traps. The writers think to themselves, if I were a student, what mistake might I make on this problem? Then they make all the wrong answers, the answer a student would get if they made that mistake. Rankine cycle problems on the FE exam are loaded with unnecessary distractors.
Ignoring distractions is not my strong suit.
So skill of the chapter, and honestly, skill of the whole course, identify the component, pick the two enthalpies that bound it, and then plug into the SFEE. Done. Big picture time, TA Serenity. Thermal efficiency of the whole power plant. It's the same definition we've been using since chapter 2. What you want divided by what you have to pay for. You want net work out. You pay for heat into the boiler. The second law guarantees this number is less than 1. And remember from chapter 6, the ceiling is set by the temperature gap. So to push efficiency up, you raise T hot or drop T cold. So, real world scenario. 2 US submarines, one up north spying on Canada, one down south spying on the Bahamas. Which nuclear reactor would operate more efficiently? The one in Canada or the one in the Bahamas? The one in Canada. The colder the ocean, the lower TC. So the more efficient your power plant.
Bring me back some poutine.
All right, example problem. So part A, the isentropic cycle. Start with pump work. We have liquid water, so we'll use the shortcut. That work of the pump is 8.07 kilojoules per kilogram. Now for turbine work, we'll have to look up H3, 3399.5, entropy 3, 6.7266. If it's isentropic, then S4 is equal to S3. So state 4 at 10 kilopascals is a wet mixture, so we're gonna have to interpolate. The left fraction is the entropy we know, the right fraction is the enthalpy that we need. We get H4S, the isentropic enthalpy, 2130.3, which gives work of the turbine 1269.2 kilojoules per kilogram. So to calculate heat in, to find H2, we'll use the SFEE, which reduces down to H2 is equal to H1 plus the work of the pump. So that gets us to 199.88. So heat in from the boiler, H3 minus H2, 3199.6, which gets us to then efficiency, which is going to be work of the turbine minus work of the pump, that's net work in the numerator, all divided by heat input in the boiler. So it's what you want divided by what you have to pay for it. Gets us to an efficiency, 39.4%. And notice how tiny the pump work is compared to the turbine work. 8 versus 1269. It's less than 1%. This is why a lot of textbooks will just throw pump work away in early problems. Don't do that on the FE exam, but understand why people think they can get away with it. Now, part B, a real turbine with 85% isentropic efficiency. So the pump stays isentropic, only the turbine changes. So from chapter 7, we can find that the actual work of the turbine would be 1078. So the heat in doesn't change, the pump work doesn't change, only the turbine output drops. So the efficiency is now 33.5%.
Does this mean the SAD engine from chapter 7 is now a SAD power plant?
Sorry, Indy, but yes, it is a sad, irreversible power plant. And this sadness costs real money. If a real 33.5% efficient 1,000 megawatt plant were operating isentropically at 39.4% efficiency, it would be producing 1,176 megawatts. Those missing 176 megawatts of power in North Carolina, that costs the power plant $8,800 every hour. $211,000 every day, $77.1 million per year. If engineers can optimize the turbine efficiency from 85% to 86%, then a 1,000 megawatt power plant will make an extra $5.1 million every year.
So real engineering is just chasing tiny percentages?
Pretty much. Attention to detail is the name of the game. 4 takeaways from the Rankine cycle. You have 4 components with 4 equations: pump, boiler, turbine, condenser. Each one is just the SFEE with the right terms canceled out. 2. Pump work is very small. Liquid is nearly incompressible, so most of the action is in the boiler and the turbine. 3. The TS diagram is your friend. Vertical pump, horizontal boiler, vertical turbine, horizontal condenser. The enclosed areas equal net work. And 4, isentropic efficiency is where real-world losses live. A turbine at 85% drops overall plant efficiency by several points. Small component losses add up to large dollar consequences. All right, so y'all have seen TA Serenity sleep through like this whole video, whereas Indiana's always got all sorts of kitty business to do. He is my best thermo study buddy. So I have a question for you. Who is your best thermo study buddy? Whoever you are thinking of, send them this video. If you don't, they're going to be bugging you all semester long, asking you a million questions. But if you send them a link to this video, I'll explain it all for you. And with all the time you save, you can get extra sleep, play more video games, whatever you want. Have a great day. Good luck on your next test.